In this section, we're going to look at work done by a torque, work done by a torque for a rigid body rotating about a fixed axis, all right? So now suppose we have, let's say, the following rigid body, and let's say it's rotating about this axis, okay? Suppose this object is being acted upon, let's say, by the following force. Let's say it's the tangential force. It's the circular path over which it's rotating, and let's say under this force it is displaced by a small distance ds over here, okay? So these are linear quantities. If you remember, work is force times distance, okay? So since this tangential distance and this force are in the same direction, we can say that the work done to just displace it by a linear distance of ds would be dw equals tangential force times the small arc length ds over here, okay? But ds equals the r perpendicular times d theta, right? So you've got dw equals the tangential force times the perpendicular distance times d theta, okay? But force, this tangential force times the perpendicular distance is torque, okay? This tangential force divided by perpendicular distance is torque. So you've got this amount of work done in displacing it by small angle d theta is torque times d theta, okay? It follows that the total work done in displacing it by a certain angle would be the integral of this value, let's say from theta initial to theta final, okay? So we have the following formula. Work done by torque equals the integral of torque integrated with respect to the angle going from initial angle to a final angle, okay? So this is the formula for the work done by a torque, okay? Now, if the torque is a constant, we can take it out. If the torque is a constant, that is, if the angular acceleration is uniform, we can take it out. So you get the following formula. Work equals torque, the integral of d theta from theta I to theta final, which should be torque times theta final minus theta initial, okay? Or we can simply say work equals, torque, work equals torque times delta theta, okay? This is provided torque is constant. If torque is constant, all right? So that's how we calculate work done by torque. Now let's look at the analogy. Remember, for linear motion is force times distance, right? Let's say delta S. So for rotation motion, this goes in torque and this goes into delta theta, okay? So the formulas for linear motion and angular motion are symmetric, all right? Now we're going to look at the work kinetic energy for rotational motion. Work kinetic energy theorem for rotational motion. For linear motion, you remember the formula was the net, this for linear motion. For linear motion, the formula was network equals change in kinetic energy over half m v final squared minus half mass initial square. Okay, now for rotational motion, just using analogy, we expect the formula to be like this: half mass goes into moment of inertia, right? Linear speed goes into angular speed. Okay, so we expect the formula to be like this: moment of inertia, omega initial square. Remember, mass is to linear motion as moment of inertia is to linear motion, and linear speed is to linear motion as angular speed is to angular motion. So we expect this formula, but let's derive it. Okay, so we've got the following formula: work equals the integral of torque d theta. Okay, but as we have seen before, torque equals moment of inertia times angular acceleration. We're talking about rotational motion about a fixed axis. Okay, but alpha, or the angular acceleration, is the derivative of angular speed with respect to time. Okay, so we have work equals the integral of moment of inertia times alpha times d theta equals the integral of moment of inertia, and then alpha is the derivative of angular speed with respect to time, and then times d theta. Okay, let's write this way now: the integral of I d omega, let's bring this dt over here, d theta by dt. Okay, but d theta by dt is simply angular speed. Okay, so you've got the following formula: work, actually we're talking about net work done, so let me put net over here. Net work done is the integral of the moment of inertia, and then we have this angular speed, and then dw. Okay, dw. Okay, this is an integration over angular speed, so this goes from initial angular speed to final angular speed. Okay, so now we can take out the moment of inertia is a constant, so you've got the integral from omega I to omega final omega dw, but this one is omega squared over 2 going from omega initial to omega final. So you get the following formula: the net work done for rotational motion is half I omega final squared minus half I omega initial squared. Okay, but so we have this formula, but if you remember, this is a formula for rotational kinetic energy. Okay, you've got kinetic energy rotational equals half I omega squared, so we can write this one also as, this is half, no, not half, kinetic energy rotational final minus kinetic energy rotational initial, or delta K. Okay, so you've got the following: net work done equals to the change in rotational kinetic energy. Okay, so this is the work kinetic energy theorem for rotational motion. This is the work kinetic energy theorem for rotational motion about a fixed axis, for rotational motion about a fixed axis. It simply states the net work done is equal to the change in rotational kinetic energy, all right? So this is the work kinetic energy theorem for rotational motion. Now let's look at an example. Suppose you have the following disk rotating about about an axle. Okay, let's say I've got an axle over here going through the center over here like this. This is the axle but it's rotating. Okay, so this is rotating but the axis. This is a disc. This is a disc. Let's say a disc of radius, let's say maybe 0.2 meters, and mass, let's say 2 kilograms, is rotating, let's say about an axle, of radius, let's say maybe 0.02 meters or 2 centimeters. Okay, so the radius of this one is 2 centimeters and the radius of the disc is 20 centimeters or 0.2 meters. Okay, suppose this disc started with a speed of let's say maybe 10 radians per second, and let's say it was stopped at a time interval of 10 seconds. Okay, because of the friction, the force of friction between the axle and the disc. Suppose the disc started with a speed of, let's say, 10 radians per second and was stopped in, let's say, 5 seconds uniformly, because of friction between the disc and axle, between the disc and axle. Okay, all right, so the question is, A, calculate the work done by friction. That's the only force involved over here. Calculate the work done by friction. The work done by friction. Okay, so the only force stopping this disc is the force of friction. So you can say W net in this case equals work done by friction. This is work done by friction. Work done by friction. Okay, and using the work kinetic energy theorem, we can say that the work done by friction equals the change in kinetic energy, the change in rotational kinetic energy, and that is half I omega final squared minus half I omega initial squared. Okay, now this axle is rotating about its center of mass. You see, this is the center of mass of the disc, so we can say this is moment of inertia about the center of mass. Okay, now for a disc, ICM equals mass times 3d squared divided by 2. Okay, now we're told the mass of the disc is 2 kilograms. Okay, so M is 2 kilograms, and we're told the radius of the disc is 0.2 meters. So you've got R equals 0.2 meters. So we can calculate the moment of inertia. The moment of inertia about an axis passing center of mass will be 2 times 0.2 squared divided by 2. Okay, that's going to be 0.04 kilogram meter squared. So we have the moment of inertia, and we're told the initial angular speed is 10 radians per second, 10 radians per second, and the final 0 because it brought to rest. Okay, 0 radian per second. and we'll stop it in 5 seconds. Okay, so that's all we need. Well, we have also time, but just 5 seconds. All right, so let's calculate work done by friction. Equals half ICM omega final squared minus half ICM omega initial squared. Plug in the values. We've got, well, let me factor out this one first. Half ICM omega final squared minus omega initial squared. Okay, so you've got half, this is 0.04, and then omega final is 0 minus 10 squared. Okay, so that is negative times 100, I think it's just going to be 2 joules. So this is the work done by friction. Now B, let's say calculate the force of friction. Calculate the force of friction between the disc and the axle okay. All right, so we can also calculate the work done by friction in a different way. Okay, it's we can use a formula work equals torque times d theta. Okay, so we have work done by friction also can be written as torque times delta theta. Okay, now the torque is, you see, you've got the force of friction, and the perpendicular distance is the radius of the axle. Okay, so you've got the axle over here, you've got the force of friction over here, so the torque due to friction is the force of friction times the radius of the axle. Okay, so we've got torque equals the radius of the axle times the force of friction. Okay, the force of friction times the radius will give you the torque. And we're told that the radius of the axle is 0.02 meters. Okay, so this is 0.02 meters. All right, so we should say the work done by friction would be negative because the force and displacement are opposing each other, so let's put a negative over here. All right, so the work done by friction is the negative of the radius of the axle times the force of friction times delta theta. Okay, now we have to calculate delta theta, the angular displacement from the information given. Okay, the information given is omega initial is 10 radians per second, omega final is 0 radians per second, and we're told the time taken is 5 seconds. Okay, so we have the following formula: delta theta equals omega I plus omega final divided by 2 times time. Okay, so omega initial is 10, omega final is 0, divided by 2, time taken is 5. So this 5 times 5, 25 radians. Okay, so this is delta theta. Okay, and we have already calculated work done by friction. Work done by friction was calculated here is negative 2 joules. Negative 2 joules. Okay, so let's go back over here. We've got omega work done by friction equals the radius of the axle times force of friction times delta theta. This one is negative 2. The radius of the axle is 0.02. The force of friction we don't know, and this one is 25. Okay, so the force of friction is negative 2 divided by well, it's -2 times 25. Okay, so this is 2 over 100, so it's going to be 4. So the force of friction is 4 newtons. Right. Now let's consider another example. Suppose we have this situation. Let's say we have a pulley, which is a disc. Okay, this is a disc, and we have two objects over here. Let's say this object is, let's call it M1 equals 10 kilograms. Okay, and then we have another object resting on the ground. This is the ground over here like this. Okay, let's say it's M2 equals maybe 5 kilograms. Okay, let's say the mass of the disk is let's say 0.2 kilograms. This is mass of disk, or pulley, you can say. And let's say the radius of the pulley, R, is also, let's say 0.2 meters. This is radius of disk. Okay, so if this is, let's go from rest. The question is to find its speed by the time it reaches the ground. Okay, so if the 10 kilogram object is let go from rest, calculate its speed by the time it reaches the ground. Okay, so we want to find the speed over here. Let's say V final. Okay, over here. All right. So we're going to use the principle of conservation of mechanical energy. Okay. But we have three objects involved. You've got linear kinetic energy of this one, linear kinetic energy of this one, and rotational kinetic energy of the disk. So the energy includes three parts: linear energy for this one, linear energy for this one, and rotational energy for the pulley. Okay. So we're going to say mechanical energy initial equals mechanical energy final. Okay. So this has got linear kinetic energy, so it's going to be half m1 v1I squared. Okay. This one is also linear, so we're going to have half m2 v2 initial squared. But this one is rotational. This is the pulley is rotating, so it's going to be half its moment of inertia is rotating about an axis to the center of mass. So, and then omega initial squared. So this equals the final energy, which is half m1 v1f squared plus half m2 v2f squared plus half ICM omega final squared. Okay, now they're all starting from rest, so we have v1I equals 0, v1I equals 0, and v2I equals 0. Okay, the pulley is also starting from 0 angular speed, so omega I also equals 0. Okay, omega I is also equal to 0. All right, Oh, I forgot to include the gravitational potential energy. Okay, let me write again because I didn't include gravitational potential energy. Okay, now we're going to use this coordinate system over here, so that means the y is 0 over here. Okay, so we're going to need this height too. Let's say this height over here is maybe 2 meters. Okay, the height between the ground and this object is, let's say, 2 meters. All right, let me write again. So you've got mechanical energy initial equals mechanical energy final, and that is kinetic energy initial plus gravitational potential energy initial equals kinetic energy final plus potential energy gravitational final. Okay, now we have 3 objects, so we've got kinetic energy for 3 of them. So you've got, this is half m1 v1i squared, okay, and then it has potential energy, which is m1 g y1i, that's its potential energy. For the second object, we have half m2 v2i squared, and then it has potential energy m2 g y2i, okay, and then you've got the rotation of the pulley, that is plus half moment of inertia by an axis passing center of mass times initial speed squared. Okay, that equals half m1 v1 final squared plus m1 g y1 final plus half m2 v2 final squared plus m2 g y2i, and then this one doesn't have potential energies being supported by the axle. Okay, so what do we know? The initial speed is 0, so we've got v1i equals 0, also v2i equals 0, they're all moving with the same speed, equals 0, and then also the initial angular speed is 0, and if you put our origin for our y-axis over here, y2i is also 0. Okay, so you've got y2i is 0, but y1i would be 2 meters. Okay, y1i would be 0. No, y1 would be, I mean, this distance over here is y1i, so that's going to be 2 meters. Okay, how about y1 final and y2 final? You see, by the time this reaches ground, its y coordinate will be 0, and the y coordinate of this one will be 2 meters. Okay, so we have y2 final. y2 final is going to be 2 because it will be over here by the time it reaches the ground. This is 2 meters. y1 final is going to be 0 because it's going to reach the ground over here. All right, so let's make these substitutions. v1i is 0, this goes away. v2i is 0, this goes away. wi is 0, this goes away. And then y2i 0, this goes away. Okay, how about on this side? We have y2f, this is f over here, so y1f would be 0, so this would be 0. That is, by the time this gets over here, its y coordinate would be 0. Okay, so let's simplify this equation. This implies, now on this side I have only this one, m1 g y1i equals half m1 v1f squared plus half m2 v2f squared plus m2 g y2f. Okay, now all these objects are moving together, so they're going to have the same speed. Okay, So let's just put let V1F, which is equal to VTF because they're moving together. VTF, let's say just use V for this one. Okay. And so with that we have the following: M1G Y1I equals, okay, so I'm going to factor out half V squared over here. So we've got half V squared, and then of course we have M1 plus M2 over here. M1 plus M2, and then we have the gravitational potential energy of the second object, right? M2 G Y2F. Okay. Now these are also equal, they're just replacing. So let's just say Y1I equals Y2F equals Y. Okay. So you've got M1 GY. Well, okay, let me go a step further. Have V squared M1 plus M2. Oh, I don't think I carried the, where is the, I didn't carry this one. ICM omega final squared. Okay, so you've got half ICM omega final squared. That's the kinetic energy of the pulley. So we have plus half ICM omega final squared. Okay, so we have this one from these two, and then we've got M2GY, and then plus half ICM omega final squared. Now remember, well, let me put omega final squared, but remember omega is speed divided by the radius. Okay, so you can just put V over R over here. But let's take this to the other side. So we've got the following. We've got to factor out YG, and then we get M1 minus M2. Okay, that equals half V squared M1 plus M2, and then we have this one plus half ICM, and then this is V over the radius of the axis of the pulley squared. Okay, so now we just have simplified this one. Okay, and for a disk, this is M R squared over 2, right? So let's just simplify this expression. So you've got, let's just take this one, half ICM V squared over R squared equals half times MR squared over 2 times V squared over R squared. Okay, so the R squared goes away, and so we get M over 4 V squared. Okay, that's what this term over here is. All right. Okay. So now I think let me just put the numbers from this onwards. So Y is 2 meters. Okay. So you've got 2, gravity approximately 10, and then M1 minus M2, I think 10 minus 2, right? This is 10, oh, 10 minus 5. So this is, I'm plugging the numbers over here. This is 10 minus 5 over here. 10 minus 5 equals, and then we've got half V squared, and then you've got the sum of the masses, 10 plus 5, okay? And this one, we just simplified it, is M over 4 V squared, okay? Plus M, well, let's put the mass of the pulley. The mass of the pulley is 0.2 kilograms. So we can just put over here 0.04 v squared. Okay, that's it. And then we just have solve for b. So you've got, this is 20 times 5, that's 100. So this side is 100. And now we can factor out v squared. So I've got 15 over 2 from here. And then over here, this is 1 over 5, maybe 1 over 20. Right? So this is simplification. So this is 300 over 20. Okay. So that's going to be 100 equals b squared. I mean, this is times 10, so that's 150 over 2, so it's going to be 151. 151 over 20. Okay, so v squared equals 100 times 20 over 151. Okay, and then of course the speed would be square root of that one, so v equals square root of, well, 10 will come out, and then we've got 20 over 151 meters per second. All right. Okay, next we're going to look at angular momentum. Okay, let's look at angular momentum. Angular momentum is a measure of the rotational motion energy an object has. This is a measure of the rotational motion, not motion energy, rotational motion an object has. Okay, an object has. We talked about the linear momentum. Now we're going to talk about angular momentum. Okay, so this is a measure of the rotational motion an object has. So let's see how we can define it. Okay, on what factors does it depend? Okay, for example, let's say we have this rod over here pivoted over here. Okay, and we've got an object, let's say it's moving with speed v. So let's say its mass is m. So this has linear momentum mv. Okay, let's say it hits it, and then this is pivoted over here. Okay, then it's going to rotate. So how much motion energy do we get out of it is the question. So when this object hits this one, you see it depends on where hits it. You get more motion, rotational motion, when you hit a higher distance over here. If you compare the amount of motion you get if you hit the object over here versus over here, you would get more rotational motion if this distance is bigger. So we can define it to be proportional to the distance from the point of rotation. Okay, so the momentum is going to be proportional to the distance between the point of rotation and the point of impact. The greater the distance at which this object hits this rod, the greater the amount of rotation. So you can say that angular momentum is proportional. Angular momentum is proportional, and this, at least in this example, is proportional to the distance between the pivot, or the point of rotation, the point of rotation and the point of impact. Okay, the point of impact. You get more rotation when this hits at higher distance than when it is at lower distance over here, right? So it is proportional to the distance between the point of impact and the point of pivot. Let's say call that distance r. Okay. All right. Now let's look at this amount of motion. Let's say it is in this direction like this. Let's say this object is moving in this direction. So by the time he's like this. Now this is a pivot. Now let's look at the two components. You remember this m times velocity. This is momentum. So basically we're talking about momentum over here. Okay. Now let's see about the effect of this impact on the rotation of this object. You see, you can decompose it into p perpendicular. I mean, this is the momentum perpendicular to this one. Okay, p perpendicular, and this one is a component that's parallel to the rod over here, or to the position vector. You see, this component, if you hit this way, you can rotate it by hitting it this way. It's only this component that is going rotated, the component that's perpendicular to the rod. Okay, so we can say that angular momentum is proportional to the component of the momentum is proportional, let's say angular momentum is proportional to the component of the linear momentum that is perpendicular to the position vector of the point of impact with respect to the point of rotation, with respect to the point of rotation. Okay, so that's what we're saying now. Is proportional to this distance over here, which is, let's call it the distance r over here, and then the perpendicular the component of the momentum is perpendicular to this position vector over here. So we can define, we're going to use L for angular momentum. This is proportional to the distance and to the component of the linear momentum, which is perpendicular to the position vector. Okay. Now, if the angle between this vector, I mean the position vector over here is theta, the angle between the momentum and the position vector is theta, then we can say p perpendicular equals p sine theta. Okay, if the angle between r, now the position vector and the momentum is theta, then we have p perpendicular equals p times the sine of theta, where p is the magnitude of the momentum. Okay, p is magnitude of the momentum. Okay, so we have angular momentum equals r p sine theta. Okay, but p equals mass times velocity, right? So you've got the angular momentum equals mass times velocity times the radius times the sine of theta. Okay, Now we can also look at r sine theta. If you extend this like this, you see the perpendicular distance. This also equals to r sine theta. This perpendicular distance over here. These two angles are equal, so this distance over here is also r perpendicular. So r sine theta also equals to the perpendicular distance between the momentum and the point of rotation. Okay. Now you can see that r sine theta is equal to the perpendicular distance between the point of rotation and the line of action of momentum. Okay, so if you want, you can write it like this: L equals m v r perpendicular if you want, or if you want m r b perpendicular, doesn't whichever, but I think this one is more popular than this one. All right. Okay, so that is how we define momentum. All right, now let me look at this definition over here. Let me put that in a box. This is mvr sine theta. Okay, this is the definition for magnitude of momentum. Okay, so L is magnitude of momentum. So let me just, let's say this is the point of impact over here. Let's say this is a point of rotation or pivot. This is, let's say, the point of impact. So let's say we have this momentum over here. This is P. This is position vector. This is momentum. Okay, so L is magnitude of momentum. And mv is magnitude of momentum. mv or P is magnitude of momentum. Okay, and what is theta? Theta is, let's say, the position vector. This is theta over here. Theta is angle between the position vector and the momentum. Position vector and the momentum. Okay, so we have the following now. This equals, let me use P for this one. So we get P r sine theta. Does this formula look familiar? You see, you remember the definition of A cross B? The magnitude of A cross B, if you remember, is magnitude of A, magnitude of B, times the sine of theta. You see the same over here. So this is the magnitude of R cross B. So this implies this angular momentum over here is the magnitude of R cross P. Okay, actually the vector momentum is defined to be R cross P. So this implies we can define the angular momentum to be R crossed with linear momentum. Okay, or with P equals mv, we can also define it as L equals m r cross v. So this is the definition of angular momentum. Is the cross product between the position vector and the velocity. Okay, its magnitude is given by this one, and this is a general vector formula for the angular momentum. So you can calculate the magnitude using this formula, and then you can use either the right hand or the scroll rule to determine its direction, right? Now let's look at an example. Let's say a particle of mass, let's say maybe 4 kilograms, is moving, let's say, with a velocity of, let's say, maybe 2I minus 3j meters per second. Okay, calculate its angular momentum with respect to a point of rotation by the time it is located, let's say at maybe 3-5 meters with respect to the point of rotation, Okay, so what we have over here is we have the velocity, which is 2I minus 3j meters per second. Its position vector with respect to the point of rotation is 3 in the I plus 5 in the j meters, and the mass is 4 kilograms. Okay, and we want to calculate its angular momentum. All right, so the angular momentum is mr cross v, and that is 4 kilograms, and then the cross product between 3I plus 5j crossed with 2I minus 3j. Okay, that's it. We just have the cross product now. So we have 4 times 3I cross 2I is 0. 3I, well, I cross j is k, and then you've got negative 9 in the k. How about the 5? J cross I is negative 10, negative k, so you've got minus 10k, and then of course j cross j is 0, so that's it. So you've got, this is negative 36 in the k direction, minus 40 in the k direction. Well, we can add them together, they're parallel, so that's negative 76 in the k direction. Okay, so this is the angular momentum with respect to the point of rotation. Okay, the negative of course means the rotation, the tendency of the angular momentum is clockwise. Okay, now we're going to look at angular momentum of a solid object rotating about a fixed axis. Angular momentum of a solid rotating about a fixed axis. Let's look at let's say a particle rotating in a circular path like this, and then we'll generalize. Okay, so let's say the speed is v. Let's say this distance is r perpendicular. Okay, let's say its mass is m. Okay, so its angular momentum is, you see, this is a position vector, this is mv, they're perpendicular to each other. Okay, this is a position vector that are perpendicular, so it'll be well, the angular momentum is, you got r perpendicular, you got the speed, you got the mass, and then the angle is 90 degrees, a circular path. Okay, sine of 90, so this is basically m v r perpendicular. Okay, the angular momentum of this particle about this axis, about the axis passing through the center of the circle. All right, but we know that v equals angular speed times the radius. Okay, so with that we have m angular speed times r perpendicular times r perpendicular. Okay, so we get m r perpendicular squared times omega. But yes, remember this m r perpendicular is moment of inertia. Okay, so the angular momentum of this particle is moment of inertia times angular speed. Okay, now this is the general form, but let's generalize for a solid. Okay, let's say it's rotating about this axis, so you take a small dm over here. This is r perpendicular. Let's say its velocity is v. So the moment of inertia, this is rotating a circular path, just like this one over here. Okay, so you can say that dl is dm r perpendicular squared times angular speed. Okay, it's just like this one over here. Okay, so the total angular momentum is the integral of r perpendicular squared dm times angular speed. Now all the masses is rotating with the same angular speed. Okay, so we can take that out. So this is the integral of this is r perpendicular squared dm, but this is the moment of inertia of the solid about the axis of rotation. Okay, so the formula for angular momentum is simply moment of inertia times angular speed. Okay, that's how we calculate angular momentum. Okay, and the direction of the angular momentum is in the direction of the axis of rotation. Okay, so we can say direction of L is along the axis of rotation. All right, so that's the formula for angular momentum for a solid rotating about a fixed axis. Now let's look at an example. Let's say we have the following rod. Okay, let's say it's rotating about, let's say the length of this one is, let's say maybe this one is 2 meters. Okay, suppose it's rotating about this axis over here. Okay, let's say this distance over here is 0.25. Okay, it's rotating by this axis, and let's say the rod shown has a mass of, let's say, 2 kilograms and a length of 2 meters. It is rotating about an axis zero 0.5 meters away from the left end, let's say with an angular speed of, let's say 10 meters per second, 10 radians per second. Okay, the question is calculate its angular momentum. Calculate its angular momentum. Calculate its angular momentum. Okay, so this is rotation about a fixed axis, so we can use the formula moment of inertia times omega. Okay, so we're given omega is 10 radians per second. We have to calculate the moment of inertia. Now the moment of inertia about an axis passing through the center of mass can be obtained from tables in textbooks. Okay, and that is ICM. ICM equals ml squared divided by 12. Okay, that is the moment of inertia about an axis passing through the center of mass, which means this over here is 1 meters. Okay, and how do you calculate the moment of inertia about this axis? We can use the parallel axis theorem. For that, we'll need this distance over here. You see, so from here to here is 1. So this distance is 1 minus 0.5 or 0.75. Okay, so this is 1 minus 0.25 or 0.75. Okay, so from the parallel axis theorem, implies the moment of inertia equals ICM plus m d squared. Okay, so our d is 1 minus 0.25, that is 0.75. Okay, and the ICM is ml squared over 12 plus m d squared. Okay, so let's plug the numbers. The mass of the rod is 2 kilograms. I've got 2. Its length is also 2 meters, 2 squared divided by 12. So the mass is 2, but the distance is 0.75 or 3 over 4. Okay, squared. All right. So this is, we've got, well, that's 4 times 2, 8 over 12. 8 over 12 is by 4, 2 by 4, 3. And then we got over here 9 times, well, this is by 2, so that's, this is 16, so we can get 8 over here. So that is 9 over 8. Okay, 9 over 8. Well, we can add them together. If you use 24 over here, so that's going to be times 8, 16 times 3, 27. That's going to be 43 over 24. So that is the moment of inertia. Okay, that's it. Then we have L equals I times omega. The moment of inertia is 43 over 24 times angular speed 10. We have, well, 430 over 12, or I mean over 24. Well, this is 430 over 24, or we can divide this in 215 divided by 12. This is going to be kilogram meter squared and then radian per second. Okay, so that is the angular momentum. All right, next we're going to talk about principle of conservation of angular momentum. Principle of conservation of angular momentum. First I'm going to state it and then I'm going to prove it. Okay, so this principle states that if the net torque acting on an object is 0, then its angular momentum is conserved. Angular momentum is conserved. Okay, in simples, if tau net equals 0, then initial angular momentum equals final angular momentum. All right, now to prove this, first let's find the relationship between angular momentum and torque. Now you remember the principle of conservation of linear momentum. The relationship was force equals the derivative of momentum with respect to time. Okay, so with analogy you would expect the relationship to be torque equals the derivative of angular momentum with respect to time, okay? But let's prove it. We have the following. L equals mass times the cross product between position vector and velocity, okay? So let's find the derivative. It's actually equals to torque, okay? So dl by dt equals mass is a constant, the derivative of r cross v, okay? So now we're going to use chain rule. So you've got mass. First we're going to have dr by, products rule, not chain rule. First we're going to take the derivative of this one, keep this one a constant, dt cross v, and then plus r cross dv by dt, okay? Do you remember what this is? dr by dt is velocity, okay? But dr by dt equals v, and as you remember, a vector crossed by itself is 0, so it follows that this one is 0 over here, okay? So we have the derivative of angular momentum with respect to time just gives you the second term. The second term is mr cross the derivative of the velocity with respect to time. But what is the derivative of velocity with respect to time? Okay, that is acceleration. All right, so you've got dl by dt equals mass r crossed with acceleration. Okay, let's write this one like this: r crossed mass times acceleration. What does mass times acceleration represent according to Newton's second law? But mass times acceleration is force acting on the particle. Okay, so dl by dt equals position vector crossed with force. But if you remember, this is torque. So you've got torque is equal to the rate of change of angular momentum with respect to time. Okay, so we have this relationship. In words, torque is equal to the negative, not negative, to the rate of change of angular momentum, Okay, now let's see what happens if tau is 0. If tau is 0, then you've got the derivative of momentum with respect to time is 0, okay? And then we cross multiply, we have dl equals 0. We integrate this from initial angular momentum to final angular momentum, we get final angular momentum minus initial angular momentum equal to 0. That is final angular momentum equals initial angular momentum. This is the principle of conservation of momentum. So we just prove it. If torque equals 0, then the final angular momentum equals the initial angular momentum. Okay, that is the principle of conservation of angular momentum. If net torque acting as object is 0, then its angular momentum is conserved. Okay, now let's write this formula for an object rotating about a fixed axis. Let's say for an object rotating about a fixed axis, we know that L equals moment of inertia times angular speed, okay? So dl by dt would be the derivative of the product of moment of inertia in angular speed with respect to time, okay? So if that equals 0, that implies d of this equals 0, and then you integrate this, you get I omega initial equals I final omega final. Okay, so this is the formula to use if you're dealing with an object rotating about a fixed axis. Okay, so this is the general one, but this one is for the case where an object is rotating about a fixed axis. Now let's look at an example. Now let's say a disk of, let's say, mass 2 kilograms and radius 0.2 meters is rotating about an axis through its center of mass. Okay, so we have the following. We have this disk. It's rotating about an axis through its center of mass. Now we're going to drop another disk. Another disk going to be dropped on the disk. Okay, another disk let's say of radius, maybe of mass 1 kilogram and radius 0.1 meter is dropped on this disk, and they both start rotating together. Okay, I should give the speed over here. About through the center of mass, let's say with an angular speed of, let's say, 10 radians per second. Okay, calculate their angular speed. Okay, so what happens is, so this one is rotating by itself. Okay, so the moment inertia is only the moment inertia of this object. So we're going to use this formula. I moment equals I final omega final. So what do you know? The initial angular speed is 10 radians per second. Okay, how about the initial moment of inertia? Initially only this one is rotating, right? So we just need it is moment of inertia. So this would be the mass of the first object, it's called m1, times its radius squared. This is the formula for the moment of inertia of a disk. Okay, so that's the moment of inertia. Its mass is 2. Its radius is 0.2, and then divide by 2 squared. Okay, so this is 0.04. So that's the initial moment of inertia before the other object joined it. Okay, 0.04 kilogram meter squared. But later both objects rotate together. Okay, so the moment of inertia is the moment of inertia of the first object plus the moment of inertia of the second object. Okay, so we have already calculated this to be 0.04. For the second object, the mass is 1 kilogram and the radius is 0.1. So this is 1 times 0.1 squared divided by 2. Okay, so this is 1 half is 0. So this is 0.04 plus I think 0.005. So this is 0.045 kilogram meter squared. So that is the final moment of inertia. Okay, so we're going to use now this formula: I omega I equals I final omega final, and then plug the numbers. You got 0.04 times 10 equals 0.045 times omega final. It follows that omega final is that is 0.4 divided by 0.045 radians per second. So you got 0.0 radians per second. So this would be speed. Since the moment of inertia increase it, its angular speed will decrease.